The VAE learned to generate by being careful. Our next idea generates by being competitive, pitting two networks against each other in a duel. One tries to forge convincing fakes, the other tries to catch them. From that contest comes some of the most realistic synthetic imagery ever made. These are generative adversarial networks. A GAN is not one network but two with opposite goals. The generator's job is to create fake data that looks real. The discriminator's job is to tell real data from the generator's fakes. They're adversaries, each one's success is the other's failure, and by competing, they drive each other to get better. The generator starts from pure random noise, a vector of nonsense, and transforms it into a candidate image. At first, its output is garbage, but it has a teacher, the discriminator. Every time its fake gets caught, it learns a little about what gave it away and adjusts. Noise in, fake out, improving with every round. The discriminator is just a classifier. It's shown a mix of real images from the dataset and fakes from the generator, and it must label each one, real or fake. When it's right, it's rewarded. When it's fooled, it learns from the miss. It's the critic that makes the whole system work. Now the duel. The generator trains to fool the discriminator trains to not be fooled. Each step both update in opposite directions. A minimax game. As the discriminator gets sharper at spotting fakes, the generator is forced to make better ones, push and counter push round after round. The classic analogy, a counterfeiter and a detective. The counterfeiter prints fake money, the detective learns to spot it, so the counterfeiter improves, so the detective improves again. Locked in this escalating arms race, the forgeries become nearly perfect, good enough to fool an expert. That's exactly the GAN dynamic. And that co-evolution is the magic. Neither network is told how to make a good image directly. The generator never even sees the real data. It only ever learns from the discriminator's feedback. Yet, through thousands of rounds of this contest, blurry blobs sharpen into strikingly realistic results. Competition is the teacher. In theory, there's a finish line. When the generator's fakes become truly indistinguishable from real data, the discriminator can do no better than a coin flip, 50-50. At that equilibrium, the generator has effectively learned the real data's distribution. It's now producing samples that belong. At their peak, GANs produced jaw-dropping photorealism, entire galleries of human faces of people who never existed. Indistinguishable from photographs, they drove super resolution, turning blurry images sharp, style transfer, and turning sketches into photos. For years, GANs were the state of the art in image generation. But GANs are notoriously hard to train. The two-network balance is delicate. Let one overpower the other and learning collapses. And there's mode collapse. The generator discovers one fake that reliably fools the critic and just produces that over and over, losing all variety. Taming a GAN is as much art as science. Set them side by side, GANs produce sharp, vivid images, but are unstable and offer no tidy latent space. YEs are stable and give a smooth, navigable space, but tend towards softer, blurrier output. Two different bargains for the same goal, generating new data. And a third approach would eventually outshine both. GANs proved that networks could generate genuinely convincing, novel content, and they dominated for years. But their instability left an opening. A newer method would arrive, easier to train, even higher in quality, and take the crown for image generation. That method works by a completely different principle. So that's the GAN, a generator and a discriminator locked in a duel, each making the other better until the fakes become real enough to fool anyone. It was a brilliant, combative idea. Next time the approach that overtook it, generating images by patiently removing noise, diffusion models. See you there.